can start now. Okay. It's a pleasure to be here, to be able to talk at the first FGC IPM joint number 3 meeting. And I'd like to give a special thanks to Ihan for organizing this. So my talk will be about the generic fiber of the exterior power morphism and the Lubin-Tate tower. Okay, so this is part of a long-term joint project with Elena Mantovan, and the idea of the project is to construct cycles in the cohomology of the Rappaport-Singh or Lubin-Tate towers using the exterior power morphism, which I constructed a few years ago. So this exterior power morphism, they go from the Lubin-Tate tower to the Rappaport-Singh tower. So I will explain this in details later. And so today I would like to, what I'm going to talk about today was, so I wanted to know the behavior, or we wanted to know the behavior of the exterior power morphism with respect to the period morphism and the Lubin-Tate and Rappaport-Singh tower. So maybe I should write something. So again, everything will be explained later. So the exterior power morphism goes from the Lubin-Tate tower to the Rappaport-Singh tower. Okay, and derivation with this, and so this is a tower, and on each tower we have the period morphism. So this goes to project to the space. This the period morphism on the Rappaport-Singh tower goes to some flag varieties, and we have, and we have a natural map from the PN to this flag variety. And the question was whether this diagram was commutative. Okay, and so this was the idea of the talk today. So the result I'm going to talk today, and so in order to understand this, we have to understand the generic fiber of this exterior power morphism. We know more or less the special fiber of this morphism. So this morphism, the exterior power morphism, as you will see later, is defined integrally. So these towers are integral objects. They are defined over. So these are defined on ZP underlying the completion. But the point is that the period morphism, these are rational morphisms. So these are defined on the generic fiber of these towers. So we have to understand the generic fiber of this morphism. But the point is that, as you will see later, the definition or the construction of the exterior power morphism is given using the modular interpretation of the Lubin-Tate and the Rappaport-Singh towers. And so we wanted to know, okay, what can we do? I wanted to know what we can do. And it seemed that the best tool here was to use the description of Schultz and Weinstein of the Rappaport-Singh tower in terms of chaotic hash theory. So this I will also explain later. And then I realized that if I can show that a certain diagram is Cartesian, then I would get first of all a generalization of a theorem of Schultz and Weinstein. So the proofs are somewhat similar, but the methods are very different. So, and secondly, I would get the commutativity of this diagram. Okay, so the main goal is to prove the following theorem. So I would like to prove this theorem. So let H or FP bar a P divisible group. And so instead of P bar, one can take any algebraically closed field of characteristic P of height H and dimension 1. Then, so let me first write this diagram. So when we have a Cartesian diagram, and please interrupt me if you have any questions. Then this diagram is Cartesian. So probably this doesn't make any sense to you now. So I'm going to define all these objects and morphisms. Okay, so I would like to prove this, and maybe I should say that if so when R is equal, so R is any number, so I can say R is any number between H and 1. When R is equal to H, then this is Schulze Einstein. Okay, so they have proved this. This is a special case. Okay. And so are there any questions? So I'm going to define all these objects and morphisms. Okay, good. Ingredients. I mean, this is a joint number theory meeting, so, and the speakers and the audience are very wide, diverse in terms of what kind of number theory they do. So, and I was thinking what, I mean, how much detail I could give, but in 1 hour, it's really very hard to provide enough details. So please ask me any question. If some objects or something you haven't seen before, at least maybe I could give some vague motivation, vague definition, anything. So, but I apologize if this is too technical. Okay. So the first thing, so I'm going to first tell you what is this. So H is a P-divisible group. So maybe I should say a few words about P-divisible groups. So if you haven't seen, if you don't know what they are. So for me, P-divisible groups sit somewhere in between abelian varieties where you have a very rich geometry, and on the one side, and on the other side, you have the homology of the abelian varieties where you have basically not geometry, but you have linear algebra. So P-divisible groups for me sit somewhere in between. I mean, they are in their own, they are very interesting, but I think the main motivation comes from abelian varieties. So, and you can think of them as a inductive system of finite flat group schemes. So you have inclusions or the chain of finite flat group scheme of a specific order, and you go to the top, and so the limit is a P-divisible group. So we know, I mean, so this we have a P-divisible group. I want to tell you what is this exterior power of the P-divisible group. Okay, so first thing is, so I want to tell you what this is. So this is theory of mine. So let G over S, so S is any scheme, and G over S is a P-divisible group of height H and dimension, it's most 1. And again, R is number between 1 and H. And then there exists another field group on the RAG with the following properties. So the first one is that the construction is functorial in G. And second property is that, so we know the height of this. So the height of the exterior power is this binomial coefficient, H to R, and the dimension is H minus 1 choose R minus 1 times the dimension of this. So the dimension is a locally constant function on S. So it, at some point it could be 1, at some point it could be 0. So and we have this formula for the dimension of lambda RG. So the third property, which is really the main property which makes everything work, is that there exists a universal alternating map lambda from R copies of G to this. And I don't want to give the exact definition of what this lambda R is or what alternating and universal means, but as I said, G is a limit of finite class group scheme. Think of each of those finite class group schemes as a FPPF sheaf on S, and lambda would be a system of alternating morphism of FPPF sheaves, and universal means like a categorical universal property. Okay, but I don't want to. It's not important what it means, but it's important that it exists, and we have this, and this makes everything work. For the existing canonical isomorphism. This and TPG. This is the Tate module of G, and you can think. I mean, this is a Tate module sheaf of G, and if you know what Tate module of Abelian variety is, you would know what this is. So this is inverse limit. Maybe I should write it. So this sends S or base T, any S scheme T to the inverse limit of, so you have the Pn torsions of G, and evaluate the T, and take the inverse limit. Okay, so this is a sheaf of free ZP modules. Okay, and fine. If you have alpha is a Drinfeld level structure. This is a very technical definition, but as in the case of a Abelian variety, when you want to, for elliptic curves, you want to put some level structure. So here you want to somehow trivialize the Tate module. So, but there's a precise definition of a Drinfeld level structure. I don't want to get into it right now, but this is important. So if alpha is a Drinfeld level structure, you can take the exterior power of alpha and using the isomorphism above, this gives you a map to TP of this. And the statement is that this is the composition is again the Drinfeld level structure. Structure finally, if S is a spectrum of a perfect field, So when you have a perfect field, then you can talk about the Dieudonné module of Pfizer groups, and we know exactly what the Dieudonné module of on the RG is. So this is canonically isomorphic to. So I'm writing the properties of the extrovert that I'm going to use. Okay. And there's a fancier way of writing this in terms of stacks, but let me just keep it like this. So are there any questions about the construction of the extrovert? Okay, good. So I have defined, so we know what H is, so we know what the extrovert is. Now I'm going to define this tower, so the Lubin-Tate and the Rappaport-Singh tower. Okay. So Rappaport-Singh. Or Lubin-Tate. And Lubin-Tate is in the case of dimension 1. So in the special case, when G has dimension 1, you say Lubin-Tate. With general Pfizer groups, it's a Rappaport. Okay, so fix Pfizer group over FP bar again, and then so let's call this K. Okay, the Pfizer group and of height H. So dimension can be anything. Okay, then we have this functor Mg from the category of nilpotent WK algebras to sets. So WK is the ring of integer of the maximal unramified. So if so this is really, in my case, this is DP unramified completely. Okay. And so I want to define a functor from the category of nilpotent. So nilpotent means that P is nilpotent. So the WK algebra is where P is nilpotent. So you send R to the set of pairs gamma and rho up to isomorphism, where gamma is a Pfizer group over R, and rho is a, so you have R but P, then you have G over P. So, and rho is really a quasi-isogen. It's not a morphism, it's a quasi-isogen. From the gamma, so the special fiber of gamma to the basis of G to R at P. Okay, so you have this functor, and there's a theorem of Rappaport and Singh that this functor is representable by locally a finite type formal scheme over SPF. So it's a formal scheme over the formal spectrum of WK. So this is not just a functor, it's the geometric object. Okay, and then we can, so this is just level 0, so no level structure, just the Pfizer group and quasi-isogen. And then now I want to add a level structure, so I want to go to the towers. So what is this? So maybe before I say, so if you know Shimura varieties, what they are, so these are moduli spaces of abelian varieties, and you can add level structure to the abelian varieties, so you have a tower of Shimura varieties, and if you go to the tower, you have the whole tower of Shimura varieties or moduli space. So, and if you think of Pfizer group as local counterparts of abelian varieties, so objects that capture the p-adic behavior of abelian varieties, then Rappaport-Singh spaces are local counterparts of Shimura varieties. So they capture the local behavior of Shimura varieties. And this can be made more precise, but just think of them as moduli of filter groups with level structure. So this I want to define a functor from. I'm going to tell you what this is. Just let me just write this down. And if you cannot read what I'm writing, please let me know. So this is the category of complete affinoid algebras or this affinoid pair. So this is, I mean, I'm going the description of, I'm going to use the description of Schultz and Wittgenstein. So it's not surprised that all these additive spaces show up here. So I sent a pair. So I have a affinoid, complete affinoid algebra, RR plus. I send this now to the set of triples. Where so this is something that comes from level 0. So, but I have to think of it in the additive space world. So I'm going to tell you this, what is this? What this is? So Mg add eta. So this is the additive generic fiber of Mg. So whenever you have a formal scheme, you can addify it. There's an additive a scheme, additive space associated with it, and then you can take the generic fiber. So I'm not going to tell you what this is exactly, but just this is in the additive world, this is the generic fiber. Okay, so because we know what Mg is, we know the additive generic fiber, and then gamma rho should be so R plus. And the new thing we have is alpha. So alpha is the level structure. So it goes from CPH to the Tate module of. So again, Tate module of gamma is you can think of it as a formal scheme and it's a sheet. So you can addify it, take the generic fiber, and alpha. So it's a morphism like this, such that whenever you have a point of R plus, so K is in the field, then alpha of X, which goes from here to you want this to be an isomorph.
Hadi, is WK the ring of vectors?
Yes, yes. I think I said it. So I mean,
okay, because there was a question in the chat. Sorry.
Okay. Maybe someone should help me with the chat. Sorry, I'm not seeing the chat box. So I mean, K is FP bar in this talk. So WK is the ring of bit vectors, but this is EP unidentified completely. So this is the tower. So this is the Rappaport sync tower. And I said if the emission of G is 1, we call it the Lubin-Tate tower. And this is a tower because you can really, instead of having a level structure at CP, you have finite level structures. And then you would have a really finite coverage. Questions? Okay, so this is done, this is done, these objects are done. Now I'm going to tell you what's H tilde is. Okay, so we're getting it. So universal, so G tilde. So this is the universal cover. universal coverage. So if R be a ring and P is topologically important on R, G over R is a p-divisible group. So I can think of G as a functor from nilpotent. So our algebra is very P is nilpotent. So maybe I should write this. So there are many different ways of looking at P as a group, but so I can think of it as a functor from nil R, and I send any R algebra S to the now direct limit of G Pn S. Okay, so this is a sheet. And I want to this I can associate another sheet G tilde from this part out, and here I send S to the inverse limit of GS. So GS is an abelian group. We take the inverse limit with the transition morphisms or multiplication by P, and this defines another functor. What we have to know is that, so this is the sheaf of QP vector space. And I'm just writing the properties we need. So there exists an isomorphism, canonical isomorphism. So if you have the Tate modular G, you invert P. So TPG is a sheaf of ZP, free ZP modules. You invert P, and you get the universal cover. If G and H are quasi-isogynous, so if you have quasi-isogeny between G and H, then this gives an isomorphism. This is, I think, very clear. The universal covers. And finally, if R is a perfect field, then so G tilde is, as I defined it, is still over R, but there exists the unique lift of G tilde to WK. So to the lifts uniquely to WR. And I still denote it by G tilde. Okay, so this is the universal cover of G. Now I want to define the exterior paramorphism. So now all objects are defined. Right, so let me go back to the diagram. So I think now all objects are defined. So this is the H copy. So this is a sheaf. You can addify it, take the generic fibre. Same here. So these are products of some copies of this thing. So every object here is clear. Now I have to tell you what is homomorphism. Okay, so I want to define so as I said, this is defined using the modular interpretation of MH. So I have a triple. So it picks the complete affinoid algebra R plus a triple gamma rho alpha on it. I want to send this to a triple here. So let me just. So if I have gamma, then the exterior power makes sense. This is another p-divisible group. Rho is the isogeny between the special power of gamma to H, and by factoriality, if you take the extra power of like quasi-isogeny, you get a quasi-isogeny between this and this. So this also makes sense. Now I have to tell you where the level structure goes. Okay, so I have to tell you what this is, and more or less we know what it is, what this is. So yeah, alpha from. So we have this level structure. This is alpha. So you take the extra power of this. This goes to just take the extra power as groups, but by theorem. So so there's a canonical morphism from this to sorry. Okay, and so this composition I see denoted by lambda r. Okay, and by theorem this is really a level structure. Okay, so this morphism lambda r is also defined. Now so I want to now to define the bottom horizontal morphism. So, okay. So I want to define this one. So the point, so in order to do this, one has to understand the behavior of the universal cover with respect to taking alternating morphisms. Okay, so there's some lemmas, so that there exists a canonical map from. So if you look at all alternating morphisms from, so fix the group G. So G is fixed. So G and X are previously groups over any basis. So you can look at all alternating morphism from R copies of G to X to the exist to the alternating morphism between the universal covers, and then this also maps to generic fibers. So and most of these results hold for multilinear morphism instead of alternating morphism. But the focus here is on exterior fibers, so I'm only talking about alternating morphism. So we have this canonical morphism, and so now if we apply this to our universal alternating morphism from R copies of H is the fixed Friese groups over K, 50 bar. So I said that we have a universal alternating morphism. So you apply this in this case, lambda, then you would get the morphism, alternating morphism for R copies of H tilde add eta to this. Okay, but this is not quite what we want. So this gives a morphism from H copies of this to H choose R copies of this. How does this work? So you pick H sections of this functor, and maybe I write this still by lambda here, or lambda tilde maybe, and then choose any indices I1 to IR between H and 1, and then repeat this. Okay, so choose R elements, R sections according to the coefficients you have, and then apply lambda tilde. Is this clear? Okay. So this is the now the bottom horizontal morphism, and now I have to tell you what the vertical morphisms are. So this goes from the Rappaport sync towers to these Hadi spaces. Okay. Again, this is a general thing. So this is what short-term violation means. So again, G is a group. I want to define this mode. So this is the this is the same paper where they classify Pulitzer groups over OC. Okay, so G or FP bar is the Pulitzer group. Height H, dimension D. Okay, and they show that this is important. They show that MG, the MG infinity, so the tower. So this is the theorem. MG infinity represents the functor so we had before one description about how they give another description of this. So so this represents the functor that on any complete affine WK algebra R plus gives the sections of this Hadi generic fiber that satisfy two conditions. Okay, so what are these conditions? First one is that the matrix. So you have a matrix. Let me write it down. Q log. So this is an element. Let me first write it down. So Q log S1 to Q log SH are H elements of the Diagonal module of G, tensor R. The Diagonal module of G is a free WK module of rank H. So this is non-canonically isomorphic to the H by H matrices in R. So it gives you have a matrix, and the first condition that this matrix has rank H minus D. So D is the dimension of G, H is its height. So this means that the co-kernel of this matrix, co-kernel of the matrix I denote it by W, is a projective R module of rank D. And what is Q log? Definition is technical, but this goes from G add R plus to, and you have to use the logarithm of the universal extension of G. So some technical definition. So, but you have a morphism from the G add eta to the Diodora module. You apply this on your SH sections. You have, this gives you a matrix. The first condition is that it has a precise rank, so H minus 2. And the second condition is that for every generic point of R, this sequence so this is given by S1 to SH, and then you apply Q log quasi-logarithm. So remember, when you take Q log, so W was the cokernel, so it lands in W. But you have to transfer the C. You want this sequence to be exact. Okay, so these are the two conditions. How does it work? So how do you go from one description to the other description? So more precisely, so if you have a triple, this, I have to tell you what are the H sections. Okay, so you use the alpha to and as I said, the Tate module of gamma sits inside the universal fibre. And then you use rho to identify this with the universal fibre of G. So here you use rho. And the S sections you get are the images of the base system. So this gives you S1 to SH that satisfy one and two. Okay, it's important for later. So this is how you get from the old description of the reinforcing tower the new one in terms of Hadi Hedayatzadeh. Okay, and one should know that in this description, this W that we have is canonically isomorphic to the Lie algebra of God. Questions? Let me go back to the diagram we had, the theorem. So now everything is defined, right? So, and I have to tell you, I have just to prove this. I have 15 minutes to prove that this is Cartesian. Okay. So the idea of the proof is so a sketch of the proof. But the idea is to cut the diagram in two parts and show that each of these two diagrams that we get are Cartesian. And I want to separate the two conditions. So this is a refined version of the result. That each condition gives you a Cartesian diagram. So what do I mean? So I have this exterior morphism that goes to I want to insert something in between. So I call this MH1 and M. So these are given by condition 1. So sections. Let me not write this. Just like this. So sections that satisfy condition 1. Okay. So the elements. I mean, the story of Schultz and Weierstrass say that elements here are sections of this that satisfy two conditions. Now I only consider condition 1. Okay. And then there's a lemma which says that this exterior morphism factors through this. So I still get a morphism like this. Okay, so and this means that I now have two diagrams. Okay, if I show that these two are Cartesian, then the whole diagram is Cartesian. I've got it. Okay, so so we first show that we show that 2 is Cartesian. How do we do this? So let me just give you the idea. So the first ingredient of the proof is compatibility. So the compatibility of the exterior morphism and Q log. Okay. So, I mean, in the description of, I mean, what is condition 1? So in condition 1, there's a Q log showing up, and I show that the construction is in some sense compatible with the construction of the exterior fiber. And the second condition is some multilinear algebra. Okay. And the point is that one has to use the property of the exterior fiber that the exterior fiber of the Dieudonné module of G is the same as the Dieudonné module of the exterior fiber of G. And then there's a relation between Q log and the Fontaine's map. Maybe I quickly write it somewhere here. So if you haven't seen this doesn't probably make any sense. If I can fit everything here. P equals plus F equals. Can you read this? Is it too small? Okay, if you cannot read this, please let me know. So there's a Fontaine morphism theta of R here, and Q log is a morphism here. So, and there's a lemma. It said that this is commutative, and this is an isomorphism here. And so I want to show that lambda R and this are compatible. So I can ask a compatibility with lambda R and this. And then there is some multilinear algebra which says that yes, they are compatible. And once you have this, you can show that this diagram is Cartesian. Okay, you have to show that if I have section here, they satisfy condition 1, if and only if when you go here, they satisfy condition 1. Okay, and then this is these two items would do the work. Okay, and then, so maybe the more interesting thing is to show that the second, or the first diagram is Cartesian. Okay, show that is Cartesian. Okay, and so again, let me just list some ingredients. Okay, so what goes in the proof? So we have to use the description of the vector bundles and the far content care. So vector bundles and the far content care. So in the new business of perfected geometry, there's this far content curve, which I can give a whole semester about this curve, but the point is that the vector bundles on this are somehow classified p-diesel groups, or the isocrystals to be more precise. Okay. So this is the proof for the, to show that the diagram is Cartesian, one has to use some geometry. Okay, so we go to the far content curve, and then the second thing is that the exact sequence that shows up in the second condition, so this exact sequence is the global section of a modification of vector bundles on far content curve. Okay, so let me write it down. So the short exact sequence in 2 is the global section. Global sections of a modification. Of vector bundles and the far content curve. Okay. And then we have to show that that's a functor. So there's a functor from isocrystals to vector bundles and the far content curve. So maybe I write the far content curve x. So x now is fixed is the far content curve. So there's a functor like this, which is essentially surjective, and actually on objects is a bijection, but it's not quite fully faithful. And this functor, I show that this preserves alternating morphisms. Okay, and so if you have a piezo group, it gives you an isocrystal, and this isocrystal gives you a vector bundle on X, and you can take the exterior power of this vector bundle, or you could take the exterior power of H, take the associated vector bundle on X, and there exists a natural morphism. So it cannot go back. Okay. And now let me explain how we prove with these 3 things that the diagram is Cartesian. So the first thing to show the commutativity. So again, I have some sections. So I want to show that this diagram is Cartesian, so I have to pick a section that satisfies condition 1. I have to show that they satisfy, if I go here, they satisfy condition 2. If I'm already here, they satisfy condition 2. And the condition 2 has to do with this modification of vector models. Okay. So how do I do this? So let's pick sections. This bar sections here, and assume that this corresponds to this triple. And again, let me quickly write what this means. So how do we get the section? I said that we take the taste module of gamma. I go to this, and this is isomorphic to this, and EIs. So then the standard basis of ZP goes to SI. Okay. And so we want to show that, we need to show that the exterior power of these sections that I defined before, so they sit inside the opposing term. Okay. And to want to show this, you have to show that they correspond to, so i.e. they correspond to this triple. Okay. I don't have that much time. Maybe I quickly show you, draw a diagram and then tell you what this is, what you want. So what does it mean? So okay, this is going to be very boring, but let me just write it down. I will drop RR plus from the notation. Let's write this. Okay. So let me trace this. So if I do this, this gives me, so if I go like this gives me the, by construction, if you remember, this is this gives me lambda r alpha. So I said that, this was really the definition of lambda r alpha. I said that you take the exterior power of alpha, there's a map from this to this, and then you go from here to here, and then here, and then so this is really how you get the triple. So this was the description of lambda r and the old description of the Rappaport sink tower. Okay, but if you go this way, you go the sections lambda rs. So if you go this way, you get this section. Okay, and the point is that these two diagrams are commutative. Okay, by factoriality of everything, and so this section lambda RS really corresponds to this to the x to the power of the triple. Okay, so this shows the commutativity. Sorry if this is too technical, but now I have to show that the diagram is Cartesian, so that if something satisfies condition 2, it it should satisfy condition 2 before taking the x to the power. So my time is up. Can I have 2 more minutes? Thank you. Cartesian. So pick any sections. If you have a section, in M1, so I know that it satisfies the first condition, and pick any generic point. Generic points infinity on the curve x. Then we have this sequence that we want to check whether or not it's exact. Okay. So I said that the sequence and the second condition is the global section of a modification of vector bundle. This is the vector bundle. This is the modification. So H. So because my section satisfied the first condition, there's W. So the co-kernel of the matrix of rank H minus 3. You push it forward, you get a skyscraper sheaf on the curve X, and this gives you a modification of this vector bundle, and we want to check whether or not this is exact. Okay. Now, first of all, this is always surjective, and this composition is always 0. So the only question is whether this is injective or not, the first one, and whether this is the kernel of the spine. Okay. So we have to show that if this is in here, then this is exact for every generic point. Okay. And the point is that if you have this section lambda RS, this gives us a modification of vector. And we know that this is exact. So some V. And this V, we can really, this depends on, I mean, this is very precisely, we know what this V is. So this is given by W. Okay, but this is not important. So this is basically given by S, the section S. Okay, so we have this exact sequence because lambda RS satisfies the second condition. And then the point, and another important thing to show is that we have a commutative diagram like this. So if I take the extra power of this morphism, this gives me this, and I have a morphism from this, which is given by by this modification. And as I said before, we have this natural map here. Okay, and the point that this is commutative. And if you show this, if we have the commutativity of this and the fact that this is exact, So this means that away from infinity, this is an isomorphism. So away from infinity, this is an isomorphism. But these two have the same rank. This is an isomorphism, and then you show that, okay, it's injective. So this, I mean, the fact that this is injective implies that this is injective. And you have to work a little with what this is, what is the degree of this sheaf and everything, and then you put everything together. You show that this is exact. Okay, and this finishes the graph. Okay, I wanted to talk about the relation with the period morphism, as I said, but once we have this Cartesian diagram, the very first diagram we had with the period morphism, one can show that this is commutative. But let me stop here, sorry.
Any questions or comments? So maybe I will ask one thing. When you were, Ismail wants to ask a question, so maybe Ismail asks first. Yes.
Okay, so I'm just, maybe it's not right, I mean, a quite good question, but I'm just wondering that whether it's worth to formulate things also in the equal characteristic setup, because I mean, yeah, it looks to be quite plausible. So to formulate things over function fields. Just
I mean, thank you very much for the question. It's a very good question. I mean, I have constructed the exterior powers in the equal characteristic case as well. In fact, in the equal characteristic case, not only you have the exterior powers, you have all tensor constructions. You have tensor products. You have different p-Dirichlet groups or local Anderson modules and do the same things. But I don't know if this description of Schultz and Weidenstein exists in that setting. I mean, we have the far content curve, so most of the ingredients of the proof exist, but the description of the moduli space, I mean, you are the expert here. The description of the moduli space of this local Anderson modules or p-Dirichlet groups in the equal characteristic case, I don't know if we have such description in terms of PID question. I would say they exist. I mean, this is a very good question, actually.
Okay, so thank you. So we can talk about it maybe later. But it looks quite fascinating. So
thank
you. Thanks.
So maybe I will ask one question. When you were proving the Cartesianness of one diagram, you were using Park-Fontaine curves, right? Vector bundles on Park-Fontaine curves. So when you consider vector bundles on Park-Fontaine curves, they are related to geometric Langlands over Park-Fontaine curve probably, right? And it is apparently related with arithmetic local Langlands correspondence over QP. So I was wondering if you translate this, plan to translate these results that you obtained to the in the language of arithmetic local Langlands, or does it have any application in that direction?
Yes, thank you very much for the question. Yes, actually, this project with Elena comes from the local Langlands. So we wanted to understand, I mean, so the refined version of the local Langlands is where you want to see, okay, what superclassical representations appear in the cohomology of Frankfurt single spaces, or if, I mean, and if you are not superclassical, okay, what so it has to do with the cycles in the cohomology of Frankfurt and Lubin-Tate. So, and we wanted to see if we can produce many cycles in the homology of the Rappaport single spaces using this exterior power morphism. So we know basically everything, almost everything about the homology of the Lubin-Tate tower, but there's some conjecture like Kratzwitz conjecture about the homology of the Rappaport single spaces. And so we wanted to produce cycles, but and so we studied the special fiber of this exterior fiber morphism. So this is very nice. And if you understand the generic fiber, then we could give some geometric statements about, I mean, what happens to the cycles in the Rappaport single tower. So yes, so it comes, and all the multiplication come from the local Lagrange, but it was the first step was to see how this relates to the period morphism, because this map from the map. So I didn't talk about the period morphism, but the point is that the map from the projected space to this Grassmannian or the flag variety is rather simple. Okay, so we wanted to use this diagram to produce, I mean, if you go to homology, to produce some cycles here.
Thank you very much. Any more questions or comments? Yes, Ihsan? Yes.
Hi, in fact, I have a request, not a question. If possible, please add some references at the end of lecture that goes from the elements of theory, for example, to the current talk. And I have this request not only from you, but also from, if possible, other lecturers.
Okay.
It is, I think, it is very instructional for students that want to follow a topic.
I mean, you have. I mean, for my talk, you have to. You can see my paper, and then I think all the references are there. So it's. I mean, you can talk about this later. So it's Cartesian. I think this is the title. Diagram of Rappaport single towers. Over universal covers. It's a very long and ugly title. Gives the groups. So this is already published. So communications in number theory and physics. That is also an archive.
And also, for example, the references for more elementary things like p-divisible groups and Rappaport single spaces that are not elementary but more elementary of the type of your talk is in the references of your article.
Yes.
Thanks.
I mean, I don't know if they're elementary or not, but these are the standard references.
Yeah. Thanks.
Okay, so if there is not more questions, I will stop recording now.